Hopefully hopefully you can all hear me all right. As has been said, I'm a first-year PhD student based mostly at Newcastle University, but I'm also working with the Alan Turing Institute. So what I do is I'm working on a field called uncertainty quantification on the STEAM project, which is what the 3D bridge, where we explore sort of the statistical implications of it. So I can explain a bit more about that. But what I want to do today is just give you guys a bit of a flavour about the research that we're doing and sort of what some of the challenges are and sort of the motivation for it. Good start. Oh no, here we go. First thing I want to introduce you guys to is the MX3D bridge. So this is a stainless steel bridge that's been 3D printed using additive manufacturing technologies. So what this means is ultimately the company got some welding arms and they printed layers of steel against one another until they got a structure. So this is known as wire and arc additive manufacturing. So the real sort of interest in this from the construction industry is that you can create any sort of arbitrary structure shape that you want, and it's something that you can't just do with traditional fabrication methods very easily, where you have to form the shapes individually and create the parts. With this, you can simply print the structure along and create what you want and create efficient, maybe new types of designs that we hadn't done before. We'll get there eventually. So with any new technology, that we get new challenges. So with the 3D printed steel, we have the case where we are welding layers on layers of weld. And welding is by nature a very complex, process that is vulnerable to many factors. If you think about it, there's like various different temperatures going, heating, cooling, and the layering itself is never very consistent. And as such, this introduces like a huge amount of uncertainty to our system that we need to be aware of. I am missing a section here. Oh, here we are, sorry. So traditionally, when we model our structures, we would use something called finite element modeling, which is based upon sort of like the underlying equations. And you just put this, your bridge or your structure or whatever you're interested in into your software, and you sort of leave it to go and it solves it for you. Now this is good if we want to measure how structures behave with traditional materials, because ultimately we make a series of very sort of straightforward assumptions where we assume that the whole system is very uniform and it behaves in a very specific way. But when it comes to our uncertain steel, we can't really assume this because there's a lot of uncertain factors at play here. So just to give you guys a bit of a introduction to what we mean by uncertainty when we're talking in a mathematical sense, there's two types of uncertainty that we can broadly think of. There's what's called epistemic uncertainty, which is the unknowns that we already know about. So if we think, for example, in our bridge, the material properties vary throughout, and we can test these and find out what the properties are by testing them. But we have very ultimately limited data, so we're not entirely sure what that is. And then there's the other type of uncertainty is known as aleatory uncertainty, and that is very much the unknowns that we don't know. So an example would be that we know that in materials that defects can appear in places, but we don't know how it happens because there's a lot of unknowns in the system that we can't characterize. So another example we can talk of that's not directly related to our bridge is sort of like if we have a batch of metal pieces and we've tested a few of them for their hardness, we can say that with some degree of certainty the hardness of the rest of the batch would be that, but we can't be sure because there's a huge degree of uncertainty. So when we model our uncertainty, we can use random variables to describe both types. So for an epistemic randomness, the unknowns that we do know, we can condition our random variables based on what we know already, sort of prior knowledge that we've elicited, and on top of any data we've got using a technique called Bayes' theorem. So ultimately, all that means that we form our sort of distribution of what we believe is likely to be the values of our random variable from what we do know and what data we've gathered. Similarly, with aleatory random variables, we introduce intrinsic randomness as almost like a noise factor, or we condition it based on sort of what we believe would be a good representation of our randomness. Just to continue on the idea of uncertainty, in our bridge model that we have a big problem in that our randomness sort of varies throughout. This is a big problem because that means we can't just use a random variable to describe our uncertainty in our material properties, for example. We need to sort of vary it over the whole bridge. So we introduced the idea of a random field where we have our like random dimensions, sort of like our random variables that describe our randomness, and then our other dimensions, sort of like our spatial dimensions. So we can say here is the it's likely to be this value, but here it would be more likely to be another value. So how many random dimensions are in a field? So many fields are what we would call infinite dimensional. That would mean that in order to describe them fully, we would have to use an infinite number of random variables in order to describe them. So that's obviously a problem when it comes to modeling our 3D printed bridge, which Alastair's going to talk about a little bit more later. But we can describe it using something called a Carhonen-Loewe expansion, which is you basically just say one random variable multiplied by a function and a factor in a series of, in a sum, gives us our random field. And then we can just chop that off, so we'll truncate it, and then we get a good estimate of our random field. So now that I've given you a bit of a crash course in what some of the terms that I'm going to be referring to, let's get back to our bridge. So there's two primary types of uncertainty in our 3D printed steel. The first one is, if we look at our properties of our 3D printed steel, we see that it varies a lot due to how the metal behaves, and also there's a lot of uncertainty in our geometry of the bridge. That is like the shape of our bridge due to the welding process. So when we talk about property uncertainty, what do we mean? So our welding process, as I said earlier, is very complicated. So ultimately you get a lot of issues where when we describe our system, we have equations and we have parameter properties that we need to talk about, such as Young's modulus. So Young's modulus is a measure of how stiff a material is under elastic deformation. So it resists, when you pull a bridge or you twist a bridge, it's going to resist this. And when we have in our bridge, this varies throughout the bridge spatially. So in order to model this, what we took was some test coupons of the material which we deformed with a series of dots painted on them. And then the displacement of these dots that were recorded was used to then infer how the Young's modulus varies throughout these test coupons to create, and we use this to then form an estimate of our random field. So you can see in the image here, this is how the displacement became a model of our random field. A similar deal with the geometric uncertainty. So again, due to the welding process, you get a very bumpy surface that you can't necessarily predict from any simple model. It doesn't just follow any given pattern. So just because these are not completely smooth, we then also need to model this as some sort of random field. So these models for random geometry under development, and what we've taken effectively is we've gotten some plates of this random printed steel here, and then laser scan said field plates, and then from these laser scans we've then constructed 3D models which then are used as our data source for creating a random field geometry which corresponds with our prior beliefs about the system. These are still very much under development, as this is a much more complex problem to solve than our random Young's modulus field. So we've characterized a couple of features of the bridge here that we want to sort of we sort of know is a random feature of the bridge. So what do we do with these random features? Because ultimately, the thing we're interested in from an engineering standpoint is how strong is this bridge going to be? If we were to subject it to a load, if we were to have many people stood on it, how much is it likely to bend? Is it likely to fail? And these features that we are interested in are what we refer to as quantities of interest. So how do we get a quantity of interest from our random information we already have characterized and modeled? So what we do is we use a model, what we would term as simulator. So in terms of our 3D printed bridge, our sort of finite element models of the big 3D bridge would normally give us this simulation, because it's a model of how a bridge or a structure behaves under load or any other sort of perturbation. So here's just sort of like sort of a quick schematic where you sort of have your uncertain inputs, you'd put it through a simulator and get sort of your uncertain outputs, which would be our quantity of interest, for example, our displacement under a given load, for example, our load at which the bridge may fail, for example. So just to reiterate over the bridge, so we have our sort of random surface and our random Young's modulus field, put that through our finite element model of our bridge, and then we get a distribution of like what the output value of our quantity of interest is. So as you can see here, there's a bit of a bell curve for whatever property we've propagated through here, and we can use that to sort of inform our design process. We can use it to complement the current approach that we do with engineering, where you would design your bridge or your structure and then test it through our modeling system, and then additionally apply safety factors to it in order to make sure that the bridge is very much safe in order to account for uncertain features. So the modeling package that we use to model the bridge is called Abacus. And Abacus doesn't natively support when the outputs are random, sort of. When you define a model in Abacus, you have to say this property is this value at this point, or this is what the surface looks like, this is the geometry. These all have to be defined at runtime in order to define the model. So to combat this, there's a couple of ways you can do it. One way would be to completely rewrite your simulator, your model, so that it can take on these random inputs just as and when you want them. But the problem with this is you have to recode up a new piece of software here. And from sort of a design standpoint, this isn't very good in terms of things, because that means you have to write new programs for new problems. So it would be better to use our long-standing existing commercial software in a way that we can propagate this sort of uncertainty through our system. So what we instead propose is that you break our stochastic or random system down into a series of deterministic realizations. So we'll just have a quick look at a simple approach here. What we do is we have our random field, and we'll draw lots of values from it, so lots of examples of potential random fields, and then solve Abacus with these potential fields many, many times. And then we get and then record all of our outputs for our randomness. And then we can use that to sort of like draw a curve or a distribution of our interested outputs. And then we get a result. So this is an approach that's well used in sort of stochastic propagation of uncertainty. And it's known as Monte Carlo simulation. So the great thing about Monte Carlo simulation is it's very simple to implement, and we know that it always converges to the distribution over our quantity of interest as the number of runs becomes infinite. So at very large numbers of runs, we can almost certainly say that this is the correct distribution for what we're interested in. But this is a caveat. Unfortunately, the Monte Carlo simulation converges at a very slow rate. The error in what we're talking about would be 1 over the square root of the number of total runs, of the order of that. And for when you have a remotely complex simulation, this becomes a problem, because you need to run the simulation in excess of 10,000 to 1 million times, really, depending on what degree of error you need. So just as a quick example here, we take, say, our model for whatever we're modeling. It might be a structure, it might be something else, so who knows? It takes about, 2 minutes to run? I'm sure most of you would probably agree that's not a very long time when we're modeling a real-world system. Say we want a fairly accurate representation of our quantity of interest, then we'd run it about 1 million times. So 1 million runs of our 2-minute simulation would take just under 4 years to run, which is not very useful from an industrial standpoint because it takes far too long in order to be able to sort of get the output for anything we need. So I'll just warn some of the members in the audience now that it's going to get a little bit more technical from here for a little bit before sort of coming back into a more sort of overall view of the how the process works. So what we want to do is we want to do it quicker. So there's two approaches we could consider. So we can modify our Monte Carlo approach using what we would call a sort of quasi-Monte Carlo techniques, where you sort of sample at the most efficient points on a grid, and then you can use this to evaluate your uncertainty in far fewer runs. The issue with this, though, is it's quite poor at estimating sort of full distributions, which is what we would like to do from it as part of this research, so that we can sort of inform our uncertainty when going forward in the design for these novel new materials. So alternatively, what we could consider is that we instead create a cheap surrogate model which emulates our very complex model, where we sample the model at various points, then use that in order to inform a quick to evaluate model, which we can then do Monte Carlo simulation on very, very quickly. Save us a lot of time. What we use for, and one of the things that we're using here and considering using is something called a polynomial chaos model, which is basically a sum of polynomials together to be able to model lots and lots of different features. So this is polynomial chaos. It's basically a sum multiplied by a coefficient multiplied by a multi-dimensional polynomial, where it's just comprised of some single-dimensional polynomials. The choice of these polynomials, it's chosen from special families of polynomials that represent the random features that we want to propagate through well. I can try give you a bit more detail on that in sort of the Q&A session if you like, but suffice to say that we choose these polynomials to make them easy to evaluate and to give a good surrogate model. So ultimately the challenge here is we've constructed our model here, and then now we need to choose the appropriate values for our coefficients. And ultimately this is very much a question in itself. How do we form the most efficient surrogate, and what points do we choose to evaluate the model on so that we can create the most effective choice of coefficients to model our problem? So what we'll consider is an expectation over our quantity of interest, so effectively the mean of the quantity of the interest. So we can posit that if we can estimate this well, then the surrogate is a good approximate to the real process in terms of our uncertainty quantification. So as a result, we can choose integration rules that would describe this. So a popular choice is the Gauss integration rules. These rules are compatible with the specific families of polynomials that we've chosen to make our surrogate from, and they can evaluate the polynomials very well. But of course, these have very much a limitation. These integration rules are one-dimensional by nature. That is, they can only estimate one random variable in our random field. So what we can do is we can create a tensor grid of points to evaluate, where we've sort of chosen every possible combination of the integration points that we're going to evaluate on for every single random variable that we're describing. But this quickly spirals out of control as it scales exponentially with the number of random variables that we're trying to propagate through the system. So for dimensions more than about 5, so more than 5 random variables to describe our system, this becomes too large to be reasonable. So instead, we can consider something called a sparse grid. This is based upon various algorithms, but this one's from what's called the Smolyak algorithm, and it considerably reduces the number of points required to do an equivalent assessment. So this is a 2-dimensional grid on the right here, done by the tensor rule. So every possible combination of our integration points, and on the left is the equivalent Smolyak grid. As you can see, there's an awful lot less points in order to get our surrogate model, and that means a lot of time saved in terms of propagating our uncertainty. So how do we do this in our sort of existing pre-made engineering model? Because obviously it's all well and good evaluating this. Are we running low on time? Oh, sorry about this. I'm more than happy to talk about this, but just to quickly go over what it is, we've created a sort of a wrapper that allows us to implement these grid implementations and then runs it so that you get your propagation of your quantity of interest without having to use a whole new program. So sorry about running on a bit long there.
Join me in thanking Liam. Great, thank you. I feel very guilty, so there will be an opportunity to ask questions. If I may now introduce Dr. Ian Fleming from Imperial College London, the second, not Dr. Alastair Gregory from Imperial College London. I need my lunch. Please come to the podium. I think you'll enjoy this presentation, and then we'll move to the Q&A. Many thanks.
Thanks ever so much, guys. It's a pleasure to be here today talking about one of the Alan Turing Institute's flagship projects. So I work in a research program sponsored by the Lloyd's Register Foundation called the Data-Centric Engineering Program. And this fuses the worlds of civil engineering and data-driven approaches together. So these are some of my collaborators on the bottom line here. And it's a great pleasure to work with a lot of them on this project. So an overview of what I'll be talking about today. I'll just give you a background on the research program that I work within, and then dive into this project that I'll be talking about individually. Some of the goals and objectives of building a digital twin. What are digital twins, and kind of like give a bit of a statistical framework on them. I'll then be talking about how we can pump real-time data into them using semi-supervised learning, and then some of the challenges associated with making this into real operational software for future infrastructure. So the Lloyd's Register Foundation Programme on Data-Centric Engineering is held at the Alan Turing Institute, and it's got three main grand challenges that the research tries to kind of solve. And within each of these grand challenges are a subset of projects that researchers and Turing Fellows work within. So these are a subset of these projects, and the one I'll be talking about today is over on the top left there. Just a plug on a kind of a journal that is coming out in the next month. The director of the program, Mark Girolami, is the editor-in-chief of this journal, and it tries to publish research within this world of fusing civil engineering with data-driven machine learning. So MX3D, the kind of the bridge I'll be talking about today, was early introduced by Liam. It is the world's largest 3D printed structure. It's to be installed on a canal side in Amsterdam in the end of the year, and it's got a whole host of exciting project partners from industry to academia, including Autodesk, the Turing, and Imperial College. So this was meant to be a video. Okay, there was a promo video for the company there, but if you go online and type in MX3D, you'll see their kind of like the work that they do. It's a Dutch startup, and they hope to be a kind of a big name in additive design. So if you had watched the promo video there, you would have seen the bridge being made, and some of the load tests and material testing that went into this. Liam talked a tiny bit about the uncertainty involved in the 3D printed process earlier. But as you can see, a few of the tests are screenshotted here. So you have the kind of a load test going on the bottom, where you fill gallons of water up and put it on top of a bridge. You've got some CAD modeling for the material properties to the left. And these materials have to be tested fully before people are able to obviously walk and interact with the bridge. So the goals of building a so-called digital twin for MX3D Bridge is that we have a real opportunity with such a novel structure to be able to provide real-time information on the uncertainties involved in design, manufacturing process of the 3D printing itself, and the material properties involved with this. We'll also be able to feed back on future designs and streamline the kind of manufacturing process for future structures that use this type of manufacturing process. So a digital twin tries to form the hybrid between real-time operational data coming from physical systems and a kind of a computer model, so a numerical solver of a physical process. This could be a finite element model that Liam talked about earlier, a finite difference model, or volume model. You can see the finite element model of the MX3D bridge there. It's torn apart, so each component of the bridge, from its handrails to its span, is modeled individually, and the kind of response is aggregated into one. So obviously you need to pump some data into this kind of like computer model, and we do this via a whole host of sensing technologies. So we have some kind of like privacy friendly sensing technologies on this bridge, and everything's very kind of cheap and affordable. So we hope to scale this kind of technology to other industries and organizations. And as you can see, we've got some accelerometers, some strain gauges, load cells, and other smaller sensors such as temperature sensors. And we try and do this all without computer vision, mainly because we want to show that this technology can be very transferable to other kind of disciplines of civil engineering. And computer vision is therefore only used for verification, to check what we're doing is actually symbolizing what's happening on the actual bridge. So how does digital twins fit into kind of machine learning and AI? It's a subset of a field of machine learning called physics-informed machine learning. That's been very popular over the last few years. Its popularity is mainly due to the fact that you can kind of cross traditional data-driven ML models with physics, the physics-based approach of modeling a real system. So this could be seeing whether a solution to a partial differential equation satisfies kind of continuity and so forth. You're combining kind of the data that comes from real-life structures, so we can see some sensors attached to the MX3D bridge there, and you can see, well, if the video works, you could see two examples of finite element methods, one modeling a bridge, but I mean, you can model pretty much any physical system. So the world of physics-informed machine learning, as I've already said, is moving quite fast. Traditionally, it's been applied to kind of standard machine learning models such as neural networks and other supervised methods. And recently, it's been inferred through this digital twins, which I'll talk about for the rest of the presentation. But it's really popular in the kind of the mainstream machine learning literature as well. And there was a blog post about it on the extremely popular Towards Data Science website last year. And as you can see, here they kind of embed this physical intuition into a neural network by adding another loss function that you try and optimize in your weighting. So what exactly does a digital twin look like if we want to kind of visualize it? So it's a cross, as I've already said, between data and a physical understanding of what's happening to our system. So we have some data generating process that is feeding in observables, such as kind of sensor data in our case. This enters in towards a digital twin, and then it will trigger some kind of computer model to obviously pump out a digital representation of what's happening on the bridge at any one time. This kind of triggering process is quite an important part, and you have to learn what is actually happening on it to trigger the right corresponding simulation from your computer model. Once your computer model is kind of triggered, it then sends a simulation into the digital twin, and therefore can update the mismatch between reality and your computer simulation via prediction and inference. So some papers have come out over the past 6 months on this kind of like prediction and inference. So in the bottom two papers there, we try and come up with a statistical framework for what a digital twin will look like. And this is basically concentrating on just a finite element numerical solver, but there are plenty of other numerical solvers you can also use from finite volume methods. And you're effectively trying to update what the matrices involved in a finite element model would look like when you incorporate data and the real world generating process into that. So if you're interested, kind of read these two papers down here. So now we've got the framework for the digital twin. How do we pump the information that the kind of numerical method is conditioned against? Well, we have to use kind of event detection from what's actually happening on the bridge, so the data that we receive from our sensors. And when our data enters into the system, we can trigger what event is actually happening, whether it be one person walking, one person jumping in the middle of a bridge. These classifications then feed into an ensemble of computer simulations that then trigger the inference and updating stage in the digital twin that I showed you on the previous slide. The classifications that happen for the events on the left-hand side there have to come from some kind of supervised, or in our case, semi-supervised learning method. So for semi-supervised learning, you have a combination, a hybrid of labeled and unlabeled data. We've been working with Autodesk to harvest this data, not on the actual MX3D bridge itself, but a similar test bridge in San Francisco. This bridge is known as the Pier 9 test bridge, and it's been operational for about 2 years now, collecting employee data as they walk into work every day in Autodesk research. So we've got about 2 years worth of unlabeled data, and only up until a few months ago did we collect our first set of labeled data, simulating lots of people walking in certain patterns over this footbridge, collecting different kind of like labeled samples. The labels correspond to people, the animations and motions that people do when they walk over this pedestrian footbridge. And we had about 3,000 snippets of time series data from the various sensors for 250 different samples. So with the small amount of labeled data that we have and the large amount of unlabeled data that we have, we'd like to learn what's happening in an average scenario on the bridge and then be able to infer that back into the digital twin. So just a kind of a snapshot of some of the labeled data that we got from our kind of a trip there. We see a wheelchair crossing over on the left-hand side. This is a very smooth profile of strain. This is strain that we're seeing here. As you can see in the middle plot, we've seen a pedestrian walking, which is quite a bit noisier given the kind of traction of a footprint rather than a wheel. And we can see a pedestrian jumping on the right-hand side causes a very localized response around one sensor in particular and nothing near another sensor. The different colored lines here correspond to the different sensors picking up the response of a bridge, and this is why when you see a person or wheelchair crossing, you see some kind of time lag between your sensor outputs. So how can we utilize this kind of labeled and unlabeled data to detect which events are happening on the bridge? So we can learn which events are happening on the bridge by studying individual kind of like patterns of pedestrian movements, and these patterns are going to be known as events, and this event could correspond to, as I just mentioned, people jumping, walking, running, anything. Obviously, as these events differ in complexity, there's going to be a difference in response in how well we can classify them. And in some cases, a crowding on a bridge could mean that we can realistically only get a simple occupancy count or an average direction that the crowd is traveling in. But this might suffice in the case where you just have to trigger off a corresponding computational simulation on this. How do we do semi-supervised learning to kind of like harvest the unlabeled data and labeled data that we do have from these pedestrian interactions with the bridge? We do it via a two-stage semi-supervised approach. In the first stage, we utilize a feature of query-based similarity searches. So this is utilizing labeled data to kind of generate a basic query of what we try and look for in our sensor output. So in this case, a footstep, as you can see on the bottom row of images. And then we use unlabeled data as further matches to improve this query shape over time. So this is analogous to unsupervised clustering, obviously. So this line gives a real snippet of kind of how exactly we do this. So we use a kind of a basic query shape from our labeled data. We pass it through many different sensor outputs from the bridge all in real time. We kind of detect new matches in our data of this query shape, and then we hone down this query shape over time to make it look more representative of what's actually happening in the unlabeled data. And this query shape can be uncertain due to the noise in the data, and we can build uncertainty bands within that detection as well, and push this through probabilistic distance metrics. So effectively, we're doing something analogous to Bayesian learning. We're using labeled data as a prior. We're then building kind of a likelihood out of the unlabeled data, and then we're trying to get a posterior on what our a kind of query shape or footprint or event would look like after we've seen both types of data. In addition to this, we use another stage of using features on other spaces apart from just the raw data. So in this case, spectral and correlation-based spaces. Here you can see cross-correlation matrices corresponding to 6 different strain sensors for 3 different types of events that is happening. So on the left, you can see one person walking right to left, and then in the middle, you see the other direction, and there's an obvious flip in your cross-correlation matrices. When this is fed into the machine learning model, you can obviously see how we can detect the difference in direction. For jumping, we've got relatively low cross-correlation given the local response of the kind of event to just one sensor that that person's jumping on. So now we'll move on to a little bit about the challenges associated with storing, managing, and scaling up this technique. First of all, the data management side, we developed a compression technique to allow us to alleviate some of the computational burden associated with storing this data. As you can imagine, these sensors are collecting about 100 different data points every second, and there's a lot of them on the MX3D bridge. We would like this kind of piece of research to be transferable to different industries and different organizations, no matter what the budget is. And therefore, we would like to store as little data as possible, whilst being able to produce the maximum kind of detection and benefits. And therefore, we use some kind of time series segmentation to break up the data and store only the bits that are relevant to what we're trying to do here, which is to detect people's events from the data. So 2 snippets of time series data from one strain sensor is shown to the left there. We can kind of compress down latent data where nobody's stepping on the bridge down to just 23 compression points from 80 seconds worth of time series data. This is good at tracking baseline of the sensor data, so we can compensate for environmental conditions. But then we're not storing as much as we are on, say, the left-hand side, where you've got some footprint and it almost stores every single data point exactly. And this is because we would like to use this piece of data for the detection later on in our process. Some of the finer details of this means that we can also update this pattern over time, just like we did a few slides ago, so we can compress what's relevant at any one given time. And if you would like to read more about this, there's a paper that's just been released on this down at the bottom row there. So this is all very well in the prototype sense, but how do we scale this up for not just the MX3D bridge in operation and not just our test bridge, but also to other organizations and other disciplines within civil engineering? So we're very lucky at the Alan Turing Institute to have the research engineering group who can commercialize and produce production quality code from academic ideas and prototypes that we produce here at the Turing. So this includes producing OS open source software, using Microsoft Azure cloud storage, and we obviously want this to be very publicly transparent in the way we store and keep data, and so the kind of interaction between our data storage and the public needs to be as open as possible. What are we storing, and why are we storing it? And so we need to be very transferable with our goals. Another technique of how we're scaling up from prototype into production quality is via a mini bridge public display at the Alan Turing Institute. So this is a 1:5 scale display of the real thing in Amsterdam. And this is meant for public engagement and to demonstrate a prototype of the digital SIN software, which you can't really see from the screen, but it's behind those guys there, demonstrating the kind of event detections and feeding back into the kind of computer model of what the bridge kind of achieve with the real thing. And on that note, I'd like to say thanks ever so much for listening to me. And get in touch with the research program of the Data Centric Engineering program. Thank you ever so much. Cheers.
Thank you, Alastair. Liam, would you like to join Alastair on stage? Please drag a seat across. And any questions you have, could we take them? I could just encourage you to get involved on the Twitter conversation as well, which is taking part on hashtag Turing CogX 19. Some interesting dialogue going on there. Okay, shall I hand the microphone to you? Have you got any questions? Anyone like to ask any questions? Come on, get your hands up here.
Hello, both of what you did relied on simulations. Like, I think you both did finite element modeling. Because I can't remember the first one, sorry, but a second talk, you had that sort of like feedback inference sort of loop. Do you actually get better accuracy than the finite element? I know finite element modeling is pretty accurate anyway, but if you're doing a different like simulation and it wasn't that accurate, would you actually get more accurate than the model that you're using by using inference?
So there's two components of that. One is the calibration of parameters within your model. So your model relies upon lots of different physical and kind of mathematical parameters that control how the finite element model simulates stuff. And these have to be calibrated towards the data. So the inference massively helps in that case. A lot of these parameters are assumed quite basically in your model. So a common case is to assume what Liam was talking about earlier, so this Young's modulus as linear throughout your whole kind of system, and obviously in the real world this isn't the case. So being able to calibrate those parameters is extremely important. The other thing is realizing the digital twin, realizing the kind of mismatch between what's happening in the real world and what's happening in the digital simulation is not just important for prediction, but it's also important for, to describe what will happen in the future. But it's also inherent of describing what's wrong with your model or what's missing. And being able to explain what's wrong or missing with your model is just as important as prediction in this case. I hope that answers your question.
Would it work if you had like an approximate version of the model, or the thing you're simulating just doesn't have a computationally cheap way of simulating it at all? Would it still be okay to use what you've used because of the inference, because of the correction with the real-life correction?
There's two types of kind of methodology that is used to kind of counter this. One is emulation. So this is where you try and rely on more kind of data-driven methodology to approximate what your kind of models actually kind of simulating. But then you can also use kind of ensemble libraries of computer simulations and call on them whenever you need to. So this is the type of thing that we're trying to do here, which is to create a library of different events that will happen and to simulate those as they're happening, but also tweaking their response. Yeah.
So,
Hi, thanks for the talk. Alastair, this one's for you. I wanted to know about your approach to measuring the similarity between the time series and your event sort of grouping for the bridge events.
Yeah, so this is done kind of via kind of a real-time methodology. So we have some kind of like initial idea on what certain events look like, or in this case, what certain footprints look like in our time series data. And this can be abstracted to like kind of a multivariate query as well, because all of the network of sensors are receiving responses at the same time. And we can kind of like detect when approximate matches of this happen over time, and then we can feed this back into making our query, so what we're looking for, better, taking into account of uncertainty, and kind of improve what we're looking for over time. So this is very much a real-time kind of methodology.
Any other questions?
Thank you. So you've played with time series and sensors. Have you looked at using 3D data as your surrogate model thing? I think so. You can use neural networks to represent 3D data rather than time series. Is it like the next step? Would we to use that?
Yeah, so you could use something like recurrent neural networks to kind of infer your time series from your sensor into predicting what's happening on the bridge. However, if you're talking about computer vision, we try and stay away from that and just talk about what we can infer from ground-based sensors. Since this, we're trying to achieve something that's very privacy-friendly, that can be reproduced very cheaply, and thus we're trying to just stick to the actual raw data from the sensors. But yeah, you could feasibly stick these into like a kind of a recurrent neural network.
Anyone else at all? Nope.
From the work you've done so far, how reliable would you say these models are to do, let's say, long-term change detection, which then might inform failure prediction and ultimately maintenance planning for assets so we can better understand how to maintain them and, you know, make them more resilient and so on? What's your thoughts on that?
Yeah, so computer models within civil engineering are actually really, really good. Civil engineers have been using kind of finite element models for a long time now. So this kind of wave of data-centric engineering, as I'm calling it, is overdue, but it's not, a lot of civil engineers don't really see the point of it. However, as these additive manufacturing structures are increasing and are becoming increasingly common, we need to be able to incorporate data into them because the risk of failure is obviously much higher. We have very little understanding of what the materials are involved in kind of this process, and Liam talked about that at the beginning of the session. Being able to quantify this uncertainty, but also see how it affects our modeling procedure is vital. So this kind of data-centric engineering methodology is really, really valid for this type of kind of structure. And hopefully we see an increase in additive manufacturing in the future, and hopefully see an increase in this type of modeling procedure as well.
Can I invite Liam? Did you have a response?
Just to add to what Alastair said, I'd like to point out in terms of the uncertainty in our materials that fairly small like variations in our input values, such as like our Young's modulus, for example, or our geometry, can have huge effects on like the stability of the structure. So it can result in massive changes in how well a structure deals with loads, so forth. Take a sort of a column, for example. If the geometry of the column is sort of wiggly, that has a massive effect on how the mode of the buckling occurs. So if it had a slight thinness on one side, it would always buckle that way. But if we don't know where this thinness occurs, that's really going to have a big effect on how our buckling mode works. So it's very important to be able to quantify these things in models in order to make sure we understand how failure may occur when we have uncertain features.
Yeah, so just a quick follow-up to say, so you think that the ability to do that condition assessment, if you like, for traditional structures, if I can call that, is good enough at the moment? And it's really you need these more for the new materials? Is that basically the takeaway?
Well, if you've got a structure that doesn't have a lot of temporal kind of variability, so something that is a reasonably new structure, such as there's a lot of kind of smart road and rail bridges that have just been manufactured. Obviously, for those, the risk of damage is a lot less. And the other thing is you don't have a lot of label damage data as well, so there's not much you can harvest from a data-driven methodology. For that, civil engineering approaches such as highly tuned and calibrated FE models is probably suffices. That's not to say, though, that in the future, when these structures become older, that this kind of data-driven methodology needs to be incorporated into this. But yeah, this is very much meant for a new generation of manufacturing where uncertainty is a lot higher than traditional manufacturing approaches.
So, do we have any more questions? I can see some cheering colleagues in the audience. You're not going to put them through the grilling. Okay. Well, it just remains, I think, for me to remind you that you may meet Alastair and Liam at the back, at the Meet the Speakers, but also to say thank you very much. Fascinating work, fascinating project. Thank you for joining us today on the stage. And please join me in thanking them with a round of applause.